Welcome, Chemistry 1007. This class is just to kind of bring us up to speed. Please don't believe that everything that's in this video is going to be on the final. It's not. I will have a study guide to focus you. This is just to bring us up to speed so you are a really good chemistry student and you're learning more. Okay, so this is video one. Periodic trends for the first ionization energy. And we talked a little bit about this, and we know that ionization energy tends to increase horizontally across a period as we move left to right. Moving left to right, just as we read, the ionization energy is going to increase, it's going to become higher. There are some uh, exceptions and a little bit of deviation from the trend, but that's mostly true. Also, the ionization energy tends to decrease down a group. So as the atom gets bigger, as the atoms get bigger, we go to a bigger element, a larger and larger element. As we go down a column, the ionization energy gets less. It gets easier to take an electron away from those metal atoms and so on. And it works somewhat for the non-metal atoms as well. So we have the S and P block elements. We also have transition metals, but we tend to ignore those. The D block and the F block tend to have a little bit different variations. And so electron affinity relates, excuse me, does relate to the ionization energy and the fact that it's pretty much negative and kind of the opposite. Uh, Electron affinity increases as we go across a period, but in a more negative number, where ionization energy increases across the period and it takes more energy and is more endothermic when we talk about ionization energy, IA. So let's look at this a little closer. Ionization energy is the loss of an electron. What does it take to pull an electron away? We know going across a period from left to right, the ionization energy goes up, requires more energy typically. We know that the ionization energy decreases as we go down the table because it gets easier and easier. There's less pull by the protons in the nucleus, more core electrons to shield that metal atom, so therefore easier to pick off an electron with ionization energy. Electron affinity, the process as we see here, an electron is gained and it becomes a negatively charged species. You can hardly see that negative sign, but it is a negative on that atom. It becomes more negative across the period. So as we go across the period, we're adding protons, but we're not adding any core of electrons, and we're going to therefore increase the electron affinity. Of course, it goes down once we start going down a column instead of going across rows, and we go in a vertical fashion. It actually gets less negative, and it's not so energetically favorable, even though it is favorable because the core electrons reduce the attraction for a new electron by that atom. Okay, so fluorine is the most electronegative species. It has the highest electronegativity. You can see that from the Pauling electronegativity scale that you used on exam 4. How do we relate this? They're sort of opposite processes. Ionization energy involves removing an electron. It's endothermic. It costs something to pull that electron out of the orbit. It's a valence electron. Let's keep that in mind. Keep in mind valence versus core electrons. Now, electron affinity involves adding an electron, which is usually exothermic. So high ionization energy means an atom holds onto its electron quite tightly, and the more negative electron affinity means that atom strongly attracts additional electrons and also holds onto its electrons very tightly. So nonmetals have high ionization energy and high electron affinity, and they want to complete their valence electron shells to get the 8 to meet the 8-octet rule. We've talked about that with the metals, where they want to lose electrons to meet the 8-octet rule, or where they want to gain electrons when we're in the halogens, such as fluorine and chlorine. Metals have low ionization energy and low electron affinity, making them more likely to lose electrons. Doesn't take a lot of energy to put in to take an electron away, and it has really no need to gain an electron unless we do so in a special fashion. So electron affinity and ionization energy all have to do with how an atom interacts with electrons, whether they attract them or are willing to lose them, and what's the energy cost to lose an electron, and how attracted are they to an electron. The more attracted they are to an electron, their electron affinity is much higher, and it's much more exothermic reaction, because you lose energy, there has to be a spontaneous reason to gain an electron, and it has to be energetically favorable. So EA is exothermic. Ionization energy takes work to break that electron away. It is endothermic, right? EA exothermic, IE endothermic. Okay, so electronegativity is also related to this bonding behavior within a molecule. Is also, this all plays a role, and the shielding effect, as mentioned, is instrumental in EA and on IE. The shielding effect, which is the core electrons blocking the effect of the protons on the outermost electrons, which are the valence shell electrons. We talked about this, the effective nuclear charge equals the atomic number minus the shielding constant, which we have to look up. And we know that the shielding constant is high when we move left to right. The shielding constant goes up in a row, but in a row or a period. But we know that in a group, as we go down a column, the shielding constant goes down, and Z and Z effective become quite similar, and this kind of goes to 0. So kind of think about it mathematically. This is why you need to strengthen your math skills, so you can be able to look at these equations and understand them, not just mathematically, but understanding them mathematically and then drawing large conclusions from them. So you need good math and good abstract skills. Hydrogen, for example, they talk about here, it has a very low shielding effect. It has no core electrons. Cesium, on the other hand, has tons and tons of core electrons, all the way up to the 6th principal energy level. And so the ionization energy is very low to take an electron from cesium. It has so many of them to give away, and they're quite shielded. So easy, low energy, low endothermic energy has to be inputted to cesium to pull away an electron. Electron affinity, lower shielding, you look at this lower shielding, more negative electron affinity. Atoms with less shielding, like halogens, especially like chlorine and fluoride, attract additional electrons more strongly, and they release a lot more energy once they gain the extra electron, and it's an exothermic reaction. But when you have higher shielding, you have less pull by the protons. The protons are shielded by the core electrons, and the electron affinity is less negative. And so, which makes sense. Fluorine's very small, has low shielding, a very negative electron affinity. And if we take something larger like bismuth, which has many core electrons, it's a larger atom. It has more shielding from the core electrons and a less negative electron affinity. The protons are not able to attract the electron as well. So the electron affinity is not as exothermic. So we think about irregularities in the general trend. It happens for nitrogen and oxygen. And how do we understand this? I'm not saying this will be on the test. I will let you know through the study guide. But when we look at this, we see nitrogen, which has 7 electrons, and oxygen, which has 8 electrons due to their proton number being equal in a neutral atom. 7 protons, 7 electrons, 8 electrons, 8 protons. But we're interested here in the electron diagram. So we're looking at the 2p orbitals, which can have 3 suborbitals that can hold up to 6 electrons. And we see nitrogen, which has less one less proton, one less electron. Everything pairs up really nicely. All the orbitals have an electron in it with paired spin, which is lowers the energy. But with oxygen, we add an electron, and we actually are at a little bit higher energy when we do that. Okay, um, so we want to think about the ionization energy here. What happens? Well, it actually turns out that it's easier to remove an electron from oxygen and make oxygen by removing an electron, and we would make oxygen positive if we removed an electron, but it would look like nitrogen, and everything would be paired, and we'd have no extra repulsion, and we wouldn't have a fourth electron in the 2p suborbitals. We'd only have 3 like nitrogen, and that's not so difficult to do, to take there's 4 electrons here in the 2p orbitals of oxygen. There's only 3 in nitrogen. If we take one of them, we end up with everything unpaired, but all the suborbitals paired spin. That's very energetically favorable. This is what I'm circling right now. These 3 electrons in the 2p orbitals of nitrogen is very energetically stabilized. It just works out. You could do the calculation. It just is the happy medium for the electrons and how they interact and repulse and their attraction to the nucleus. But when you add the extra electron, that brings the energy of oxygen up a bit. And so to pull an electron away from oxygen is easier to pull this fourth electron in the 2p orbital, as opposed to pulling one of these 3 electrons away from nitrogen, which is much harder. So the ionization energy trend sort of deviates for nitrogen and oxygen. Okay. Not saying I'll test you on this. This is a good thing to know. If you take inorganic or physical chemistry or higher level chemistry, you'll want to know these things. You have nitrogen, which has 7 for the Z, and oxygen, which has 8. We have nitrogen in summation. We have a half-filled p subshell that's very stabilizing. But in oxygen, we have one more electron. So we have a paired electron in the 2p, which makes it 2p4. And so this half-filled stability is good. It is lowering the energy. And with oxygen, you have this electron-electron repulsion. So it's probably going to be easier. Oxygen is going to be at a higher energy level with that fourth electron in the p orbital versus the 3 electrons that are in the p orbital. It's going to be easier to pull an electron away from oxygen and bring it back to being half full, similar to nitrogen, which is very stabilizing. And they use an analogy here about oxygen adds a 4th roommate, and there's too much strife, and it's easier to remove that 4th roommate in the 3 bedrooms versus nitrogen, where everyone is separated into 3 bedrooms and there's no fighting. Go back to your slides and look at that. These anthropological analogies are good. They can help us. Here we see it right here. Let me point it out. We see nitrogen to the the ionization energy for removing an electron in nitrogen is 1402. That's endothermic. We have to put that energy in to strip 1 electron from nitrogen. But for oxygen, it's not so high. It's only 1,314 kilojoules per mole to strip oxygen, because oxygen will end up having a half-filled shell just like nitrogen, and that's not so bad. So that's why we have that. But then we go back up, we see fluorine, the ionization energy increases as we move left to right. And with fluorine, it does exactly what we expect. The ionization of energy is for fluorine is very highly endothermic. It doesn't want to give up its electrons, so it's going to cost a lot. As we move down the table, of course, the ionization energy gets lower. And the same is true here. The ionization tends to get lower, even with the metals, when we move down a column. But do look at these trends and know them. It's important. Electron affinity, again, is exothermic. We get energy released to the surrounding, and the stability goes up in the atom by gaining an electron. Chloride anion is more stable than chlorine that has not added an electron. And the electron affinity is negative 349 kilojoules are released because of the favorability. And nature likes chloride, not just simply chlorine. So we can say general trends in electron affinity, although there are some deviations from those trends, we can feel confident that as we go up, we shrink the atom, gets less core electrons, it gets smaller, and the electron affinity here is kind of close, but it tends to go up here. And we see that the electron affinity tends to go up because there's such an attraction for an electron because there's less shielding. Rubidium has more shielding than sodium, and sodium has more shielding than hydrogen. So it makes sense. And with less shielding, it's easier for the protons to attract the electron and therefore have greater electron affinity. As we move across a row or a period, we're not adding core electrons, so it kind of works out, but we do have that nitrogen oxygen deviation because of the p orbitals and how they're shaped, as I explained earlier. The same can be said for even phosphorus and sulfur. We have similar reasoning processes there. So make sure you know the difference. And this is copyrighted. I appreciate being allowed to do this, and I hope students get something from this. And this is Dr. Pryor, Chemistry 1007. Appreciate you guys watching today.